All right. Hey, what we want to do today is wrap up our lesson on section 5.3. We're going to talk about something called absolute area. Then we're going to slide into another little topic called average Y value. And then there actually will be an exit ticket. All of those things we'll want to complete just as if we were in the classroom. Now, the first thing I want to do is have a little discussion with you on something known as total absolute area. Now, to do this, it's really going to be helpful if you have a book and look at it with me, as opposed to just kind of watch me. There's something about the way it shows up in the book. I want you to see it. So, go get a book, page 275, and we're going to look at number 19. You know what? I actually need to go get my book too. Okay. All right. I got my book. Did you get yours? But seriously, I hope that you're looking on page 275 at number 19. When you do get there, you see what honestly appears to be, like every other problem that we've done. It looks like there's some area that's colored in that lovely blue color, and it goes to the x-axis. So what's the big deal? Well, the big deal is honestly the directions. If you do look at the directions, it's not real, it's kind of subtle, it's not real obvious, but it says find the total shaded area. Now, if I could comment, I would like that, I wish those directions were a little bit stronger. If I had written the book, I would have said, let's call it the total absolute area. Honestly, that's what it is. It's going to end up being an absolute value. It's going to end up being, in a sense, the total amount of shaded space. In other words, without any negatives. So I'm being serious. The first thing you want to just notice is that this is a different question. And it can be missed if you just kind of look at the problem like every other problem we've done. Now, if you're saying, okay, I got you. So, how are we going to do this differently? Well, one thing I'll tell you is that we're not going to be able to just kind of do the integral. In other words, to just kind of flippantly do an integral from what appears to be 0 to 4, which is like the entire interval of 3x minus x squared. And the reason that you're not going to be able to do that is because what that does is it takes into account the positive and the negative area. And it kind of gives you one big swipe from left to right. And the problem with that is that that is not the same as the total absolute area. So if we can't just do one big integral, what are we going to do? Okay, well, let's look at the problem a little bit more closely. As you can see here, I changed the colors a little bit. So that is kind of the first thing to notice, that we basically have two separate regions. One of the regions is above the x-axis, one is below the x-axis. And that kind of takes me to my first point here, that you want to not be surprised that the region that's above the x-axis, that when we eventually do this problem, that it's going to come out positive. And that's great, because that's what we expect when we're in that space. Well, in the same fashion, you shouldn't be surprised that the space that's below the x-axis, that's in red here, is going to come out negative. You also should not be surprised with that. The only thing is that we're just going to need to make it absolute. We're just going to switch it to be positive. Now, in order to do that, do you see that there's one spot that is crucial? Yes, I've been mentioning it over the past few days. It's the X-Intercept. You see, an X-Intercept, by definition, is always a place where a graph can change from being positive to negative. And so we're going to find the X-Intercept. It's actually already marked on the graph. But maybe more importantly, we're going to use the X-Intercept to subdivide. You see, the rule of thumb with these problems is that you want to make a sketch and you're going to want to subdivide. And you might want to add that you're going to subdivide with the X-Intercept. Now, perhaps some of these things seem kind of obvious, and that's good if they do. But I know that there's some problems that we'll get into later where I'm just going to say, hey, find the total absolute area. And you're going to have to do all these things. You're going to have to make the sketch. You're going to have to see the X-intercept so that you can subdivide the problem. Okay, well, let's continue. Let's subdivide this problem. If you're curious, it's really not too tricky. I hope that it would seem reasonable to say that region 1 is just going to be the integral from 0 to 3. And again, notice that the number 3 becomes one of my boundaries for this part of the problem. So region 1 is the integral from 0 to 3 of our function, which is 3x minus x squared. And then region 2, if you'd like to call it that, region 2 is going to pick up where we left off at 3 and finish the rest of the way to 4 of our function. So really, when it comes to setting up the problem, now we've basically created 2 integrals. Now, there's some things that are true about both these integrals, and that can kind of make our work a little bit easier. Obviously, what's true about them is that they share the same function, that is the 3x minus x squared. So yeah, we're gonna need a capital F of x. We're gonna need an antiderivative. So let's just find that antiderivative one time. Now, when you add to the exponent, you get x squared. When you divide by the new exponent, you're dividing by 2. So yeah, it doesn't really simplify, I suppose, like super nice, but you get 3x squared over 2, and then x cubed over 3. Remember, we decided that you don't need plus c. They're just going to subtract out anyway. The other thing to notice about this problem, again, to kind of make your life a little easier, is that when it comes to evaluating the parts of this problem, that is the values of this problem, there's really 3 values that I'm going to need. I'm going to need f of 0, I'm going to need f of 3, and I'm going to need f of 4. So yeah, maybe I'll just find all 3 of them right now so that I have them and can subtract them the right way. Notice that I did kind of write them in a different order from yesterday. I just decided to write them from start to finish. Okay, so are you doing this on your own, or are you kind of waiting for me? You're going to plug in 0. That's pretty easy. When you plug that in, you just get 0 minus 0. So it just comes out to a big old 0. When you plug in 3, it comes out to be 4.5. If you want to, I'm going to use decimals today. And when I plug in 4, it looks like my notes say that I get 2.67. Okay, now be careful because we have a lot of information here. We want to use it the right way. When it comes to getting the green region, that's going to be the f of 3 minus the f of 0. Again, f of 3 minus the f of 0. So when I carefully grab those numbers, it looks like it's 4.5 minus 0, which of course is 4.5. Oops, I said equals 0, I mean minus 0. But yeah, that just comes out to 4.5. And when I do the red region, that's by definition going to be the f of 4 minus the f of 3. I want to make sure I do that in the right order. And the f of 4 was my 267 minus, again, that 4.5. Now, it's good to write this out because now we notice, and like I said a few times, we're not surprised that the red area is coming out negative. Using some decimals this time, I'll write it as negative 183. Okay, so now what am I going to do? Okay, well, not to overthink this, but again, it's a total absolute area. I've got 2 areas. All I have to do is add them together, but in a total absolute sense. So again, my total absolute area is going to be certainly my 4.5. That was the red area. That was my region 1. And just for a little emphasis, I'm going to do the absolute value of that, although it's going to remain positive, plus the absolute value of my negative 183. Okay, and I end up with a final answer of 633, which is really 19 thirds, but since I'm using decimals, I'll stick with that. Should seem pretty straightforward, but to sort of repeat, the main difference in this problem was the directions. And you have to realize when the directions say to find the total absolute area, you're going to need a sketch so that you can see the two separate, in this case, the two separate areas, so that you can subdivide and then ultimately end up breaking it apart and finding the absolute value of that sum. The exit ticket is going to look a lot like number 18. In fact, it is going to be number 18. And, well, that one will put you a little bit more to the test. I'll say a little bit more later in the video. Let's talk about something called average Y value. I know it seems kind of random, but what we're doing is getting some applications now of integrals. And you're going to find out in a few moments that average Y values actually have something to do with area. But before we get to that, let's just see if we can find the average Y value of Y equals X from 0 to 4. Now, we're going to do this without calculus first. We're going to kind of do this by just using some good math thinking. And the place that I'm going to appeal to is the graph. Now, when you think about the graph of Y equals X, of course, it's a nice little straight line, but it contains lots of Y values, doesn't it? In fact, the Y values that we're trying to think about are the ones that are between 0 and 4. Now, again, there's lots of Y values on this graph between 0 and 4. Why don't we find some of them? Maybe we'll find the ones that are at 1, 2, 3, and 4. Okay, now those Y values, we should start at 0 since that's part of our interval. So we're going to do 0, 1, 2, 3, and 4. All right, so looks like the function's got some Y values at each of those spots. And yeah, it's not too hard to find them since the equation is Y equals X. Then we basically already know what the Y values are. But to emphasize that, I have a Y value of 0, 1, 2, 3, and 4. Now, take yourself out of calculus for a second and just kind of think about good math. If you have 5 numbers, which is what I have here, and you want to find the average of them, what do you do? Well, you know what to do. You just add them up, right? You add them up and yeah, you divide. You divide by the total number of numbers. So, by the way, everything I'm doing here is right. But in a moment, we're going to see how we can get this same answer with integrals. So anyhow, let's finish this. I think if you add these numbers up, you get 10 over 5, which is the number 2. Now, it might kind of make sense to you that the number 2 is the average Y value. It's definitely right in the middle. Of course, it works that way because this equation is very constant, or I shouldn't say constant, but it's very consistent in the way that it changes. So what do integrals have to do with this? What do integrals have to do with this average Y value? Well, I'm glad that you asked. Okay, I think that we can kind of mess around here a little bit, kind of consider a little bit of what we already know. If I could get this written out here. One of those things is that we know that there is such a thing as an integral. It's always the integral of the function, so I'm pretty sure this problem, the function is just x. And yeah, the only other thing is the boundaries, so it would seem to make sense to go from 0 to 4, which is what we should do. I wonder what this integral is. Okay, well, we could find this answer using triangles if we wanted to. I'm going to appeal to this antiderivative method just so we can practice it again. I end up with a pretty basic antiderivative, and I can plug in 4 and 0. Now, when you plug in 4, you get 16 divided by 2. That's actually the number 8. And when you plug in 0, you just get 0. So it looks like my integral is 8. Ah, darn. You thought that maybe it was going to come out to be 2, the answer that we found for the average. Well, I didn't say that it was going to equal the integral, but I said it has something to do with the integral. So the question becomes, how can we use the number 8 and one other idea that's in this problem to help us get the number 2? How can we use the number 8 and one other? You say the number 0 to 4? Well, that's correct. That is actually the length of your interval. So look, if you take the length of your interval and you divide it into your integral or your area, well, you do end up with 2. You do end up with the average. And so what's true here is that an integral can help us to find an average y value if we just divide it by the length of the interval. I have that for you here in a little bit more of a definition form. Take a look at it with me. We call it the average value of f of x. You can call it also average y value, like I was doing. So the average value of f of x, it actually turns out to be the integral. Now, that's a key part because that's what we're talking about right now. But yeah, you're going to do the integral. But you want to make sure that you always divide it by the length of the interval. I always like to add a little bit to this. Again, maybe that's a little bit obvious that that's the length of the interval. That's what you divide by. You can even say divide by if you'd like. But what if we added a little bit to this word here, integral? Like maybe the word area. Well, that would work also, okay? Because of course those are the same ideas. So you could actually divide an area by a length, and that too will equal an average y value. Ready to try it for a problem? Okay, now again, this is I'm glad that I had this here, else I would have forgot. It turns out that every continuous function, now remember, continuous just means that the function has no breaks or jumps or any funny business. So we've got a nice curve. It can be a straight line, it can be a curved line, but all continuous functions will actually attain that average. That's kind of fancy talk for you're not only going to be able to find the average, but that actual number shows up on the graph. And so did you remember how I circled y equals 2? Yeah, it not only is the average, but it's on the graph. So every graph, every function will have its average somewhere between A and B, somewhere in that interval. We're going to find that point. That becomes kind of part of these questions. So yeah, let's find an average, and let's also find the point or the place where that happens. Okay, and so the question would probably look something like this. It's going to say find the average and the point where the function assumes this average. Find the average and the point where the function assumes this average. Let's do it for sine of x. That should be fun. Okay, now if you're trying to find the average of the sine of x from 0 to pi, you don't actually need a sketch. I know I'm big on sketches, but sometimes it's good just to use the formula and understand that your average is going to have to be 1 over, in other words, we're going to divide by the length of the interval. Now the interval goes from 0 to pi, so technically if I subtract those, I'm just going to get pi. But it's going to be 1 over pi minus 0 times the integral of the sine of x from 0 to pi. Okay, so we kind of have two parts to our problem here. Like I said, I think we already know what the coefficient is. We're going to divide by pi. How about the integral of the sine of x from 0 to pi? Now we've done that one a couple times. maybe we are at a point where we can say, yeah, we did that yesterday, we did that last week. Isn't that going to equal 2? Well, yes, it is. That's always the area under one of those sine wave bumps. So I end up with an average of 2 over pi. Okay, now 2 over pi would be like 2 divided by 3.14. You kind of get an idea that it's decimal, but where does the sine wave attain that average? Okay, well now I'm going to appeal to a sketch, okay, because I have a sine wave, and that sine wave from 0 to pi has y values on it. Now again, there's a whole bunch of y values. Notice that we didn't actually find all of them because the graph is not very consistent, and that would be extra work. Instead, what we did was we just used the formula. But I do want you to realize that 2 over pi is a y value. And so that y value looks like that it is attained at 2 places. It looks like as the sine wave goes up and comes back down, that it's going to equal 2 over pi at 2 places. And now what we want to do is we want to try to find out when. Now, you could do this problem with a graphing calculator. I'm going to take a little bit more of an algebra approach because I want you guys to realize that what we're really talking about is when the sine wave, okay, not the antiderivative of the sine wave, but just the sine wave, when does it equal 2 over pi? And so we actually have ourselves a pretty simple little equation where with your calculator, you can just do the inverse sine. You can do the inverse sine of pi over 2. As long as your calculator is in radians. Oops, I said pi over 2, didn't I? It's 2 over pi. So the inverse sine of 2 over pi, and that comes out to be, now it comes out to be an x value, because that's actually what you're solving for, of 0.69. The book likes to call that a c value. Again, it's actually an x value. But there's another place, isn't there? There's another place over here on the right. Now, if I type that in my calculator again, I'm still going to get 0.69. What if we do a little bit of thinking about the symmetry of the sine wave? Isn't it true that this red distance here, again, that's 0.69, would be the same as this red distance? Yeah, so I can actually start at pi, and I can go backwards over to that other point. In other words, my other point, my other c value, would be pi minus 0.69. And since we're working with decimals here, we can just write that answer as 245. Again, that's actually the c value, if you'd like to call it that. But it's the other place where we attain the average. Okay, so there's kind of 2 answers to this problem. Again, there's the average. That would definitely be part of your answer, 2 over pi. And then there are my 2 c values that should also be clearly shown and given. Okay, that's the only problem that we're going to do with that. I'm confident that you guys can apply that principle to the previous. But just remember that to do this, you have to find the integral, and you have to divide it by the length. Okay, you have to do both those parts, and that's your average y value. All right, onward and upward to the exit ticket. Okay, now, yeah, it's number 18 from page 275. Couple thoughts here. Had you been in the classroom, this definitely would be a problem where there would be some engagement. There would be some engagement because there's some things about that blue area that are a little different. I don't want to give it all away, but some of that blue area is not, it's not between the graph and the x-axis. Okay, now you kind of have to look at it and you have to say, yeah, there's some space that is actually somewhere else. And you guys are going to have to do some subdividing And I will share just one other hint that you likely will find at least one time the area of a rectangle. Now, that rectangle is going to be either in the blue space or possibly involved with the blue space. So when I say rectangle, I don't mean the RAM method, but at some point, you should process that you need to find the area of a rectangle. There's actually a couple different ways to apply that. Okay, you can talk to each other. I actually hope that you do, but your work has to support your final answer. And I would like you to submit that today. Yes, I'm going to ask you to submit that today because I want you to get on it and I want you to process it so that we can follow up with it on Monday. Okay, yes, I want you to get it right, but it's kind of one of those problems where right or wrong, we're going to follow up with it on Monday so that you can continue to learn. All right. So that finishes up section 5.3. Hey, you can start your assignment. Actually, you should start your assignment. The work period is going to be our next class period. So that'll give you something to think about also. All right. Have a good day.